Alrighty. So today we have Eric Keller joining us from the Network and Security Research Group to share some more about his research and hopefully get you all involved. Go ahead, Eric.
Great. All right. Thanks. All right. So as mentioned, I'm Eric Keller. I'm a professor here. So I'm in the ECE department, but I also, work closely with a lot of students in the CS department. And so I've been here, I think it's 12 years now. So I have a background where I came from industry as well. I worked for 7 years before getting my PhD. So hopefully, we can meet sometime, but if not, then hopefully enjoy this hour at least. All right, so here I'm just going to talk a little bit about, kind of my research at the high level, and then I'll go into some specific projects that I'm working on that you might have an opportunity to get involved in, and just general talk like that. So I would categorize kind of my research as, fitting this mission. Like my mission is to make even the most complex network infrastructures dead simple to manage. And we want to do this through programmability. So why focus on management? And it's really because, my belief is that many issues that we have, whether it's from reliability or security, ultimately end up being people problems. So we need automation. We need a holistic programmatic management where computers can, define and verify the infrastructure that's needed. So, my group is called networking. So I work on a lot of stuff related to networking, and I always find it interesting to kind of call out networking and how it's perceived, and then kind of call out what it looks like as research. So if you've kind of seen networking, heard that term, this is really about how practitioners learn networking. So there's a lot of certification courses on how to configure specific pieces of equipment. This is largely around Cisco, and Juniper has their own certification, and now we're moving. There's some cloud related certifications, and then a lot of these practitioners just kind of follow the on the job training. If there's a problem handed to them, they go kind of search the web, try to find solutions, play around with the devices, but they kind of keep the lights on in terms of networks and make them workable. On the complementary to that, this is how colleges teach networking, and we're no different here at CU, and look at like a network systems class. So these classes focus on the OSI layers. You have kind of shown here is the Ethernet, or kind of the link layer down at the bottom, where you might have stuff like Ethernet and Wi-Fi. Kind of that middle layer is the internet protocol, and then you have layers above it like TCP, and then above that like HTTP. And then a lot of these classes really focus on sockets programming. So a client and server can open up what are called sockets, some basically a communication path between two different computers to be able to exchange data between them. So now that's great, and that forms the basis, both of those. Where my research really comes in is in exploring the computer systems issues. So we're talking the operating system, the hardware, the application software, all of that, exploring those systems issues in enabling programmability. And this is where like traditionally non-programmable systems. So if you look back a couple decades, the network was pretty rigid and static, but to enable the infrastructure we have today, it needs to be made much more programmable. Same with the computing infrastructure and so forth. And then, leveraging that programmability. And this is where, really the power, comes in. Because once you make things programmable and flexible, then you can do a lot with it. And so that kind of ties together towards a goal of a secure, reliable, efficient, easy to manage network infrastructure. Now, if you ever kind of talk to me, you kind of note that what I really like is that networks are really everywhere. So this is kind of a way to, kind of say, all right, there's a bunch of different domains that we can actually be targeting. We can, we have the internet. Certainly that's a network. But then data centers, are kind of the next big wave of where a lot of infrastructure is, being deployed and a lot of innovation is happening. We have the virtualized and containerized infrastructure and the systems that manage those and be able to interconnect all of that. We have data infrastructure. So this is where really you don't even care about the physical infrastructure, but you have, you're ingesting a bunch of data. You need to transform it some manner. You need to run queries on it. And that's basically interconnecting a bunch of different pieces of kind of data infrastructure together to form, this kind of large scale processing. And then also embedded infrastructure. So it doesn't just, kind of relate to the big, powerful, but, embedded infrastructure as well. And these all come together with, kind of the three main pillars of compute, storage, and networking all working together. So that's what I mean by networks are everywhere and these systems are complex. And my group largely works at all layers of the computing stack. We've done work in hardware, virtualization, operating systems, application software, distributed software, and management. So this is the current team. I don't need to kind of call them each out, but if you know any of them, feel free to say hi and introduce yourself. And also listed on the slide are a bunch of 5 master students that are currently doing independent studies with me, and I'll get to kind of what their projects are kind of later in the talk. All right, so a lot of times, when students that are new to research, think that there's like this set of problems where it's like, all right, what is the problem I can work on and kind of change the world type of thing. But really, I want to convey that research is iterative. So whether you work with me or you work with another faculty member, this whole idea is something that's really, really powerful once you kind of appreciate that this is the case. So a lot of times, you start with a vague idea, and it might come from your background, it might come from some reading you have, but at this point, it's really difficult to see the novelty yet of the idea. Sometimes you can get that great idea and it's see a lot of details, but that actually probably is, from extensive kind of experimentation and background on a particular topic. But what you do, and what I do with a lot of the students, is you take this vague idea that relates to a particular area that a student might be interested in, and you kind of come up with something to do, whether it's an experiment or read something or whatever it is, but just do something. And based on that something, you come back and you discuss the idea. Now sometimes great, you have great insights, you found something, like I wrote this piece of software and I noticed this part of it was really challenging to do. All right, that might be a kind of refinement. We might be finding what the real problem is. So then we refine the idea. And then in some cases, though, you just go back to the drawing board. You read something and, or you do something and just say there's really nothing here. And that's perfectly fine, because there's no shortage of ideas, especially of vague ideas. And you just kind of keep going. And so once you have this refined idea, well, then the next step is to do something. And again, you kind of keep iterating that process until you really refine in on a strong problem statement of, all right, here's, a problem that's well motivated, is going to, have importance if there's a strong outcome and all that kind of stuff. All right. So let me take a quick breather here, and if there's any questions on anything I said so far before I dive into some current projects. Nope. All right. So here's a sampling of current projects. I'm going to talk about 3 of them, and then I list also 3 others that may be of interest to some out there. So the first one is called rack scale operating system. So rack scale computing is this concept of really our kind of compute unit is a collection of servers in a rack. So think about as tall as a person, a collection of servers. And there's technologies that are coming out to be able to really interconnect them in a much kind of tighter way, but we need an operating system for them. So the alternative right now are kind of like container management systems like Kubernetes, or kind of application specific platforms that do all this management. But imagine if we could just write applications for the whole rack, and it kind of can scale across it, and we don't have to really worry about that. A second area that I won't talk about, but I'll mention here, is rethinking BGP. So if you've taken network systems, BGP is a protocol that basically runs the internet. So it's how 2 different network providers like AT&T and Verizon communicate with one another to be able to say, here are all of the different places on the internet that I can reach, and then here's the path that I would take, and then Verizon can say the same thing, and then they can know what traffic to send through what other networks. Problem is, it was designed decades ago, and it's actually worked. The internet works pretty well, but there are a lot of problems that exist out there that still need solving, and we've been putting on band-aids on top of band-aids on top of band-aids for a while now. But kind of there's some new ideas we have to be able to kind of rethink how BGP might actually work, and different aspects of it. And then finally, serverless computing, and in particular, machine learning on the training on top of the serverless platform. So serverless computing is something like AWS calls their offering of it Lambda, and it's basically where you can tell it, here's the kind of program or function I want to execute under these conditions, and then Amazon or the serverless framework is able to kind of scale out, take care of the full infrastructure. So it's not technically serverless, but from a user standpoint, I don't have to worry about servers. And so here the idea is, with machine learning, can we extend effectively the power of our laptop, where I can write some models or whatever and not have to build out a large infrastructure or manage anything like that, but just click a button, it goes out to the cloud, expands, uses serverless infrastructure, to expand out. All right, so now let me go into the 3 projects I wanted to go in a little more depth in, TNA, Ghost, and multi-cloud networking. All right, so TNA is transparent network acceleration. So really what it's about when we say network acceleration, we're talking about Linux networking. So I'm a big fan of Linux. Linux has a lot of functionality. In the kernel, it has functions like firewalling, and forwarding. It's got a whole bunch of management tools like IP route 2, IP tables, all those kinds of command line tools that maybe you hate, but they're actually quite powerful. And then there's a lot of kind of control plane software like FRR, which is a routing package that's widely used. We got Strong Swan, provides kind of IPsec tunnels. All of this is leveraging functionality inside of the Linux kernel. So really, this is a strong ecosystem, and then Kubernetes works well on top of Linux. So let's dive into Kubernetes. So hopefully everybody's at least heard what the word Kubernetes. So what it allows you to do is specify a distributed application effectively, and then have it deploy in these kind of isolation units called containers. And then there's a lot of things that Kubernetes itself as a platform does. I don't have to worry about where these different ones get executed, or how they can communicate. Kubernetes kind of can take care of that. So let's say I'm creating a deployment with three replicas of an application and what's known as a service in Kubernetes. So I would write some kind of YAML code as shown here, and then I would deploy it. So I would do like something like kubectl apply. And the first thing that happens is the scheduler, so the Kubernetes scheduler, determines which host to deploy each container on. So these are shown as pods. So pod is the terminology in Kubernetes that effectively you can think of as a container, or if you're more familiar with virtual machines, that's perfectly fine to kind of think of it as a virtual machine, but it's containers. So the scheduler will determine where to execute them. Then a network plugin, like if you've used like something like Calico or Flannel, what it'll do is it'll create virtual Ethernet pairs. So one inside of the pod, one inside the host, and then attach that to a bridge inside of Linux. So these are all it just is using Linux commands. It inserts some routing, so using like IP route, potentially running BGP process, insert some access controls through IP tables, again, all just Linux. And then if I were to deploy a service, so all the services is basically saying these three pods, I want them to act as one. So like let's say the 3 web servers, and I want to put something in front of it that I just connect to talk to the service, and then any one of the backend web servers can handle the requests. So I would launch a service, and so a service can be realized with IP tables or IPVS, again, just Linux stuff. So what all that means is if I'm using Kubernetes under the hood, a lot of Linux kernel networking is happening. So hopefully that at least kind of helped convey one use case, but there's plenty of others to kind of convey the idea that Linux networking is rich. Problem is Linux networking is slow. So this has been a problem known for decades. And there's been a lot of, kind of innovation to try to make it faster. So with this, these kind of alternate pipelines emerged. So we kind of grouped these into 2 main categories. So one we call kernel bypass. So this is, for example, running inside of user space an application that uses some libraries that allow that program to talk directly to the network cards without any involvement of the Linux kernel. So this is great. If Linux is slow, well, we've just, bypassed the Linux networking. I can rewrite it, and they did a lot of things to make it really fast. So we've gained all this performance. Likewise, there is some options to do in kernel. We call it in kernel network bypass. So these are technologies like XDP and eBPF or Click as a kernel module, if you've heard of any of those. And this is basically like load a module into the kernel, and that module can talk directly to the network card, pulling packets in kind of inside of its program, inside of the kernel. Now it can, kind of talk to some stuff in Linux, but really to get any sort of performance, you're having to rewrite what's being done, kind of in that context. So if I want to do a firewall, if I want to do IP, forwarding, I would have to rewrite that functionality inside of eBPF in this example. So in both cases, the kernel bypass and in kernel bypass or network bypass, in both cases, really we're losing all of Linux's ecosystem, and we have to re-implement all of those services just in the name of trying to get it faster, to get something faster. So we kind of set out and said, can we just make Linux networking faster rather than having to bypass it and start over? And so some insights we had is that not everything is needed all of the time. Linux is a big monolithic, a lot of functionality, but instead, let's compose a minimal data plane automatically based on only what is needed. Second kind of insight we had was that Linux mixes the fast path and slow path processing really into one data path. And so if you haven't heard these terms before, fast path in networking is normally your common case. So most of the time, all your packets are going to be handled in this way, but then there's going to be some cases where like an exception case happens. And these are typically handled on a slow path. So an example might be, IP forwarding is going to be on your fast path, but then handling, like say IP route options or ICMP packets, like ping, maybe that goes on your slow path because it's not really happening that often. So we want to make a streamlined fast path so that we can do the most common case really fast. So what we do is we noted instead, let's instantiate the fast path in a specialized execution environment instead of the one monolithic, ball of code that Linux has right now. So that's where TNA comes in. So we're going to process the common case packets with minimal overhead. So on the right, you can see, the Linux kernel, which is currently, exists. It has handles all the complex cases, so that gives us the completeness of functionality. But then we created this little thing, which we call TNA, which is a fast path, and it actually is within Linux. It leverages eBPF, but the way we use it is such that it's tightly integrated with the Linux networking stack. So let me walk through a real quick example of this. So how do we make this transparent? Where's the word transparent? Well, to the user, they're just, using Linux. So, a user could create a bridge, they can manipulate some routes, they can add filtering rules, whatever it is. All of that inside of Linux creates, kernel objects. So this is just on what happens in Linux. So where TNA comes in is we can introspect the Linux kernel. So we look at, through the APIs of Linux, we see, all right, this thing was just configured. So from that, we could build a dependency graph that represents all of these different configured services. From that, we look up inside of a library that we have of the different modules that can, kind of perform that functionality, and we compose those into a data path. So this FPM stands for Fast Path Modules, and then we deploy it into the XDP layer. So the programs are written in the language. So eBPF is basically it's kind of like, it provides like a C-like language that you can insert code into the kernel in a safe manner. So it kind of restricts, creates this kind of little sandbox-ish environment inside of the kernel by kind of compiling it dynamically. All right, so that was TNA. And, so some example projects that might, be the case here. So one thing we're interested in looking at, beyond the core system is like hardware offload. So we can compile, and we've already started, or Xilinx, an FPGA manufacturer. Well, now they're AMD. They've created a compiler that can compile eBPF programs to an FPGA, so we can get some hardware offload capabilities. But it'd be useful. We have some ideas on, kind of how you can structure the code and things like that to make it better. Another example project is video conferencing software. So shown here is a picture of something called a selective forwarding unit. So basically video conferencing. So imagine you have, kind of a bunch of different participants, but they're on, different, say, bandwidth, kind of devices. So one might be on a phone. Well, this selective forwarding unit basically is making it so that everybody, sends their videos feeds to it, and then it will distribute it out to all the other participants at the rate that is most appropriate to it. So there's a bunch of software that does stuff like that. It has, if you were to deploy this in the real world, you would want to do stuff like putting it behind a firewall and potentially matting. So, the acceleration there. But then also it itself could be decomposed and leverage acceleration. And we see some great potential there. So here, a lot of this code a lot of it is written in C++. Having a good background in Linux and networking are, kind of the useful skills there. All right, so the next project I want to talk about, and there'll be plenty of time. I'm going through these pretty fast, so there'll be plenty of time to ask questions about any of these. Second project is called Ghost. It was some catchy acronym. So it stands for something, but I can't remember for the life of me what it is. But it basically relates to 5G security. All right, so the threat that we're interested in addressing is a malicious network operator. Right, so I'm a user, I have a phone, and to use a 5G network, I have to, have service with some operator like an AT&T or a Verizon or whoever. Right. So, a lot of times you see the kind of malicious, the attacker shown as, this kind of like hooded bad guy. It's somebody wearing a hoodie that's kind of a hacker. But it's also the case where, it's just people in suits might be the case here. So, think of the power that agencies like the NSA have. They can go into network operators. And basically you say, I want to tap all of this traffic and I want to inspect whatever. So this particular project has, a kind of military use case that, like, for example, the U.S. military wanted to go overseas and, into a potentially hostile environment. One approach is to set up a private 5G infrastructure, but that's a lot of overhead and cost, and it's slower to do. But they, so instead, want to use the kind of native 5G infrastructure, but being in a kind of hostile environment, the network operators, or more, kind of likely their governments, agencies, the equivalent of NSA, in that country, would have access, to the cell towers. All right, so that's kind of the threat, and really kind of honing in. So 5G data is encrypted, so it's not like we're worried about kind of a hacker looking at the traffic and then being able to see, oh, here's my my conversations, or get all my information and so forth. But the metadata is not encrypted. That's stuff that the operators get fully full access to. So we're talking about identifiers. So you have a unique identifier in your phone. Think of your laptop has a MAC address. And so on a network, if that MAC address uniquely identifies that device. So there's identifiers that can do that. It can tell location, not necessarily like precise, like I'm not like sharing GPS coordinates with it, but kind of through the triangulation, we've seen enough TV programs where we know that that's possible. It can see your traffic patterns, so it can know like how much bandwidth you're using at what time, and all that kind of stuff. It could see the sites you visited, so it sees your IP addresses because that's ultimately its job to forward it on to those sites. And so what can you do with all of that? Well, you can do stuff like identify a kind of high value target. So like if you can profile an individual and kind of say, this is what this type of person, maybe a general, looks like, because these are the types of sites that they visit. All right, that's one thing you can do. You can see group activity if there's several kind of devices kind of moving together. You can also see like these two people kind of met at this particular location. You might see their pattern of life, like I go to Starbucks every morning at 5 a.m. type of thing. Those are all kind of valuable information to know. So we're introducing Ghost, and kind of the tagline is hiding in plain sight. So this would be software that runs both on your phone, but is coordinated through kind of a central server. And so we do things like we protect the individuals through ID or persona swapping. So ID are those kind of hard identifiers. Persona is like the patterns of like access. Like I visit these sites regularly. That kind of forms my persona. So we try to kind of protect those through swapping. So disguising, which helps disguise individuals, disguise activity patterns, things like that. We can also protect group activities through activity shaping. So, ideally we can disguise a group size or an organization or group traffic. So think of this as injecting fake traffic into the network from a bunch of different devices. And so maybe, real activity looks like this yellow graph. And then, what we are doing is injecting this black line of traffic. And then what can be observed looks kind of like a flat line. So they're not able to kind of pull out those types of patterns. And then final kind of thing we're doing is protecting the software itself through hardware security. So there's things called trusted execution environments, or TEs, to help us hide the software. So a sample use case of this. So imagine, we're calling it bump swapping. So imagine this kind of, character A or person A and person B, and this is their real path. They're walking along some path. That's what A does, and then this is what B does. Now, what we're trying to do is make it so over here on the visualization, this is what we want to make it look like to the operator. We want to make it look like the yellow or the person B kind of came to this point and then kind of turned around. And we did that by swapping the ID between person A and person B when they kind of came near each other. And so this is something we're doing to kind of confuse the operator. And why it says red team is that's kind of our own group that we have that are going to act as the adversary. All right, so one example project that one of my students is working on, we calling it vSIM. So as a quick overview of SIM cards, so I'm sure everybody's heard the term SIM card. There's a little thing that you can pop into your phone. A lot of times they come in basically embedded into the phone, but there's some manufacturer that is creating these chips that are these smart cards. They have some processing on them, and the key thing that they have is they have a secret on it, and the secret is write only. So basically, you can't read it out of it. But it's the manufacturer basically picks that K, burns it into the SIM card, ships out the SIM card for installation into phones, and then shares that K with an operator. So the operator kind of keeps this database, and how the operator would use it is basically whenever a phone wants to join a network, it contacts the operator and says, "I want to join the network." The operator then needs to validate the SIM, and so basically says, here, encrypt something, encrypt X, Y, Z. The phone will receive that. It'll pass it down into the SIM card, and this is where that processing comes in into play. And it'll say, encrypt this using this key K. And so that happens on the SIM card. It returns it in an encrypted form and then sends it to the operator. Now the operator can compare it encrypted the same XYZ with K, compares that with what the phone did, and then can say, yes, this checks out. And so now I've validated this phone, and now I can let it on the network. So what we're doing is we're creating something called the virtual SIM. So we're looking to leverage the existence of these trusted execution environments or secure hardware already present in the phones, do away with that manufacturer that was in this kind of upper left-hand corner, and instead allow the operator to kind of choose this secret, and through a mechanism to communicate only with the trusted execution environment, which makes it so that the rest of the software in the phone can't see what's going on. But then what this allows is basically an operator can dynamically provision SIM cards, virtual SIM cards, without the manufacturer, leading to a much simpler user experience. Now for Ghost, it helps us because we don't need to swap between physical devices to change our IDs. So like right now we have this kind of plug-in device into a phone that has like an array of SIM cards, and then we can kind of interface to different ones of those. All right, so this might involve C programming for parts of it, and the secure hardware, SGX or TrustZone. So SGX is from Intel, TrustZone is from ARM, maybe some Android programming, maybe a distributed system, programming, because it's a lot of, create that software in the operator. And there's also, so that's just kind of on the vSIM side, but there's also, kind of alternate projects doing network traffic analysis and modeling. If you have kind of that interest in kind of creating those models of what users are doing and things like that, there's definitely opportunities there. All right, so for the third one in the last couple of minutes, I want to talk about multi-cloud networking. So hopefully you've heard of companies like Amazon, Google, Microsoft. So they all offer cloud infrastructure, and you probably have used it. And so this is what we're really building all of our software on nowadays. So as a user, or a kind of enterprise, I need to develop applications. I'm going to take applications, so these would represent the compute part of it. They're all communicating over some network, and kind of a job of kind of creating those applications is mapping it down onto whatever's happening inside of the cloud, using all the cloud constructs to be able to create networks, create virtual machines, and so forth. There's a challenge here in that the networking piece of this is a challenge. It's a challenge to optimize the cost, security, performance. And this is because each provider has, different constructs and different interfaces, but then also because really the skill sets are changing. Like previously we had these Cisco certified network engineers, but more and more we're moving towards skill sets that are more generalists, like DevOps or cloud architect. And, networking is just, kind of one small subset of things they do. Now, this may not apply to the biggest of the big companies, that might be able to kind of have teams of just network engineers, that are cloud, capable. But for the majority of cloud users, this is a problem. So what we're doing is we're creating basically this layer in between that's bridging this gap, and it's using basically these keywords I talked about at the beginning, automation, abstractions, optimizations. There are some, kind of alternative approaches in industry, and they're kind of using what we're calling an overlay model. I'm not going to get into the details, but I'm happy to kind of offline. But really, those models really lead to performance and cost overheads that we think are not really useful, or not necessary. And but people are going to live with it just to have that ease of use. So we're creating better abstractions and better models to kind of optimize the network. So if you're interested in cloud networking, anything cloud, anything, there's kind of infrastructure as code, things like Terraform, Linux networking will definitely come into play here, measurement, optimization, all those kinds of problems. All right, so for the last topic, I want to talk about independent studies. So what's the process? What am I looking for? What are examples? So I'll start with, what are the examples? So these are the current independent studies. So these are the 5 students and what they're each working on. So working on rethinking the BGP route exchange, really looking into analyzing some network data that we have access to be able to kind of do this. Looking at the multi-cloud networking, so really pulling out and highlighting understanding the differences in each cloud. Working on TNA, so he's writing an accelerated load balancer inside of Linux. Another one is working on Freshen, which is basically creating, porting and running benchmarks for serverless so we can pull out a particular, and really quantify the impact of one particular thing that we're looking to improve. And then another is looking at rethinking the BGP security. So this is building, a cloud-based database of routing information. So that's the examples, and kind of what's the process. Really watch this, talk to me, all of these students. I met in various ways, whether they were in my class or just kind of emailed me after this, an equivalent presentation a different year. and just said, they're interested in this topic, and we kind of went through a little bit of that iteration of, I kind of said, here are some projects my current students are working on. But if a student has, their own ideas, happy to, kind of discuss those as well. And then what am I looking for? I don't even know. Certainly if you're a match to any of the existing ongoing projects, that's a great thing. But I think just in general, a strong desire to learn and a drive, a strong driven approach to kind of doing stuff. So with that, I'll conclude and kind of open it up if there's any last question or any questions in the last few minutes that we have. Feel free to pop stuff in the chat if you don't want to speak up.
Yeah, hi Rick, this is Tarun. So I didn't understand what you're doing exactly in the multi-cloud networking. So I understood the overlay part that you are telling, the extra overhead that it brings, but what are you exactly solving in that?
All right, so that's so what am I exactly doing? So I don't have a slide, the backup slides for this, but the overlay model. So there's companies like Aviatrix is the one kind of really championing this. What they do is they have you install a virtual machine inside of each of your VPCs, and then through a central controller that you also have to kind of get from them, you can kind of say, I want these different, like I want this VPC to be able to talk to this VPC and this one to talk to this. And they basically create IPsec tunnels between them, and all of the traffic goes over basically general public internet. So what that has is, well, there's performance overhead of, that. There's also the performance overhead of the network paths that they're taking. And then there's cost overheads as well. So that's the current state of the art. What we're doing is we're saying, well, we think there's opportunities for sharing resources and optimizing paths within a network, within each of the clouds. So, for example, AWS has a global infrastructure and they have a backbone network, but it doesn't all perform the exact same. Likewise, Google has those. And then there's, if we have to hop between cloud providers, there may be optimal locations, both in terms of cost and performance, where that could occur. So what we're doing, we call it the network service provider model, is we're basically creating an infrastructure on top of this, making it so that an application, all they have to do is connect to our network, and then we'll get the traffic to their destination in a kind of optimal manner. So hopefully that provided a little extra context.
Yeah, got it. Thank you.
All right, looks like we got one on chat. What applications are we looking at for 5G security, Ghost? Is there possible ways to further research on that? So the applications in Ghost are really, just whatever you would use a phone for. So I, maybe want to watch YouTube. I want to get on Slack and message people. So those are the things that, I want to be able to use a phone for. Ghost is doing these different types of things underneath the hood. And so, if you've used an infrastructure like Tor, which is kind of this anonymity network. So like Tor, and I'm not saying we're equivalent to Tor. I'm just using it as a kind of an analogy to think of. What you do with Tor is I want to visit some website, and it will bounce my traffic through a bunch of intermediate nodes. before going out to that final destination. And what Tor provided was the ability so that no single node knows the source and the destination of the traffic. All right, so it's basically doing something like hiding my activity in a network. So now we're going to do that, not exactly that, but kind of in similar type capabilities with Ghost. And this is kind of the main ones: the activity shaping, the persona swapping, ID swapping, and then getting software to run inside the trusted execution environment. So what research opportunities are there is basically all of this is kind of open. We have preliminary versions of each, but we just received a grant from the NSF and DoD to kind of continue this work into a phase 2, and so now we're getting into a lot deeper kind of things that we're doing. All right. Could you please elaborate a bit more on serverless ML? Are there any available data to predict the resources utilized for a task? Could you elaborate on what do you mean by are there available data to predict the resources utilized for a task? So I think that means, if I understand correctly, and if not, feel free to chime in, is when we launch a serverless container, so the way serverless works is basically, each function that could get executed gets run inside of a container. A framework such as AWS Lambda will, kind of monitor how much load is coming in, and then will create more replicas as needed, scaling up to as much as it needs, and then scaling down to 0 when possible. So there is a kind of current research theme that exists out there trying to predict behavior. So one of the kind of problems in serverless is called the cold start problem. So it's great that you can scale down to 0 because then that costs 0. But now let's say I get a request and I need to service it. Well, now I have to launch something, and it's cold start. So it's almost like booting up a container, which might take several milliseconds to do. And so people are out there trying to predict the workloads and when they might have to do those kinds of things. I imagine there's research out there on predicting the utilization for a given task, and that may be an easier problem because you have like a history. Like as soon as you've run something for a while, you can get a good profile on something. That said, what's interesting, like a related project I didn't talk about, we have something called Escra, and that's not necessarily, we did apply it to serverless, but it's really hard to predict how much resources a given container will need. So a lot of times people end up over allocating resources. And so we created a auto scaling framework that works at sub-millisecond kind of timescales, or sub-second, sub-100 millisecond timescales to be able to dynamically scale, vertically scale a given container. Hopefully I answered that question.
Hi, Eric. This is Abhijit. Yeah, I just had a quick question. So do you envision on using machine learning to perform ghost activities and, evade certain security measures?
Yeah, I think there's a great opportunity. So I'm not a machine learning expert, but certainly that's would be a great application if for students that have an interest in it or a background in it, in trying to both learn the patterns. So we need kind of the evaluation software. So like we need to basically build up an adversary, but then also to generate you know, kind of what that kind of fake traffic is, or, you know, kind of all the different aspects of it. So we're working with, you know, part of the team is from applied math. So we're kind of, you know, using some of those things. So, you know, there's certainly interesting things there.
Thank you.
Excellent. All right. Any last questions? All right. Well, with that, I appreciate everybody. Let me flash up the email address one last time. You know, feel free to reach out to me. Really appreciate everybody's time. And, you know, thanks to CS department for hosting me.
Thank you, Eric. Appreciate it.
All right. Thanks.
Bye.
Bye.